tetrahedral. You see the shape. It's a very common shape in chemistry, especially with carbon-based compounds like methane. Methane's a carbon-based compound. These carbon-hydrogen-based compounds, a field of chemistry called organic chemistry. You see that particular structure along organic chemistry. So we have ways, different ways we could represent it. Molecules. Here, this is a formula. A formula is like this symbolic representation. So hydrogen has a symbol H. Oxygen has a symbol O. So we have two hydrogens for every oxygen. In other words, two hydrogen atoms for every one oxygen atom. The symbolic representation is called a formula. So it's a formula for H2O. Or chemical symbol. Well, we don't call it chemical symbol, we call it formula. So, when we're looking at matter, there are different states of matter that we see in nature. You know, there's solid state, and then water is a liquid state, and air is a gaseous state. So those three states. And it turns out there are four states of matter. Do you know what the fourth state of matter is? Plasma. There are plasmas on Earth, but they're not like the sun. You know, the sun is a classic example of plasma there. But we have fluorescent lamps. Those are plasmas inside there. One way of thinking about a plasma is it's like a lightning bolt, and a fluorescent lamp is a controlled lightning bolt. Now, a typical lightning bolt is all over the place, but a lightning bolt is also plasma, as is a flame. A flame's another plasma. Water is interesting because it can easily go through three states. You know, if you cool this down, what happens when you cool it down? Well, eventually it'll freeze, right? When it freezes, when water is frozen, has all the motion stopped? It turns out no, all the motion is not stopped. You can freeze this stuff at 0 degrees C, and then if you shine the X-rays on it at 0 degrees C, you're going to see the atoms look oval in shape because they're vibrating around. So, you know, I don't want those vibrations. I don't want my atoms to look oval. So how cold would I have to get it to stop the atoms from moving? I don't want the atoms moving anymore. Would I have to cool it down infinitely cold? Okay, we would go down to not 0 degrees. We would call it 0 Kelvin. We don't use the degrees when it comes to Kelvin. It's just Kelvin. But you're right. If we cool it down to 0 Kelvin, there'd be no more motion. Now, is 0 Kelvin infinitely cold? Or is there a finite? No, it turns out it's not infinitely cold. 0 Kelvin is equivalent to minus 464 Fahrenheit or minus 273 Celsius. So it's not super cold. If we cool it down, now it's super hard to reach that temperature because there's no freezer that would do it very easily. If we cool it down to 0 Kelvin, what should happen is, you know, the atoms go slower and slower, and then we hit 0 Kelvin, or minus 273 C, or minus 464 Fahrenheit, and the atoms will stop. And once the atoms stop, there's no more motion, no more atomic motion. Now, what happens if we warm it up? You know, if we warm it up, then vibrations are going to get more, and then eventually the crystal is going to melt. The ice crystal is going to melt and form liquid water. Now, with liquid water, we got trouble because the water molecules are moving all over the place, so it's really going to be hard to capture an image. And the same thing with gaseous water. Very hard to capture an image. And so, when we're thinking about different states of matter, we think in terms of motion. And kinetic is another word for motion. I know there's some kinesiology majors. We look at motion. So, kinetic, motion, molecule or molecules. Kinetic molecular theory is motion of molecules theory. So, motion of molecules is used to better understand the different states of matter: solid, liquid, gas. So we approach things, you know, in different ways. We don't always start with observation, because if we already know the theory, for example, atoms and molecules, we can just start there. Look at this same thing here. We don't have to go back all the way to observations. There's already people who have developed kinetic molecular theory, so let's just go ahead and try to use that to better understand the states of matter. So do you know how many types of motion there are? 3 main types of motion. When we're thinking about movement, 3 main types of movement. One type of movement is vibrations. You know, the atoms can vibrate like this. Another type of motion is rotation. You know, the water molecules can rotate. And the third and final type of motion is translation. Translation, the water molecules translate from point A to point B in space. So in gaseous waters, the water molecules can translate, they can vibrate, that is, the atoms can vibrate, and they can rotate. So in gaseous. And when we look at gaseous water or steam, the molecules don't touch each other here. They're separated by some distance. When we look at liquid water, the water molecules can translate, rotate, and vibrate. The only difference here is they're touching each other. And so they're clumped together, or they're stuck together. What causes them to break free is this. As we increase the temperature, what's going to happen? Well, they're going to start moving faster and faster, and eventually, if they move fast enough, they're going to break free. It would be too hard to cage those water molecules once they hit that level of kinetic energy. However, if we want to mellow these out, we'll just cool it down. We'll cool it down, and cool it down, and cool it down, and eventually we're going to freeze it. When we get this frozen solid ice, there's no more translational motion, there's no more rotational motion. The only motion that we have is vibrational motion. That's it. So the theory has been used to help understand these states in terms of motion and kinetic molecular theory. First off, let's take a look at some motion here. It turns out that the motion is kind of complicated. It's really weird, though, because water molecules can't vibrate any way they want. You know, there are only 3 ways a water molecule can vibrate. You know that? So if you're looking at the hydrogen atoms can do this on the water molecule. They can do this. They can do one other one. Something like that. But there's only 3 ways, which is kind of weird, but let's take a look at it here. These ways are called modes.
During the unit, you'll study a system with 3 pucks. There are potentially 6 degrees of freedom here, but keeping the displacements to the line of the springs means that the symmetry of the system restricts this to 3 degrees of freedom, for which there are 3 normal modes.
3 normal modes means those are the 3 ways that that system can vibrate. That's it. Although that doesn't look like water. But you can see the vibrations. And those are different energies of
Let's
vibration.
return to the behavior of water molecules that were introduced at the beginning of this video band, and examine the way in which they can be excited by 3 particular microwave frequencies. A water molecule is composed of 2 hydrogen atoms, together with a single oxygen atom. So each water molecule is called H2O by chemists. Although quantum mechanics is the only accurate description of molecules, insight can be gained by considering a Newtonian mechanics model. You can represent the forces between the atoms as springs. Chemists usually represent molecules by what's called a ball and stick model. Now, although the water molecule has 9 degrees of freedom, which give rise to 9 normal modes, 6 of these are trivial, in which the particles move as if they're part of a rigid body. But there are 3 non-trivial normal modes. The smallest normal mode angular frequency corresponds to the normal mode where 2 hydrogens swing from side to side, each with a sinusoidal motion. Note that the oxygen atom hardly moves, since it's about 16 times more massive than each of the 2 hydrogens. A second normal mode has the hydrogens oscillating in step with each other, along the bonds, again at microwave frequencies. We should also say that in this animation, these oscillations are not only being slowed down, they're also being wildly exaggerated, as the movement would be minute compared to the length of the bond. Then finally, there's a resonant frequency in which the hydrogen atoms again oscillate in and out, but this time exactly out of step with each other. So all 3 normal modes are present in water. When it's irradiated by microwaves, the molecules vibrate, and as you saw in Unit 10, this corresponds to an increase in temperature. So the water gets hotter and hotter until it boils. Normal modes are one of the most applicable areas studied in LST 207. However, the mechanical systems usually studied are only accessible by computer.
So later on we'll learn more about this, but it turns out that not all energies are, each of those vibrations requires a certain minimum energy to cause that to happen. And so when you heat up water in a flame, it turns out a lot of the energies in the flame aren't going to do anything to water because they don't have the right energy, that is the right resonant frequency to cause those vibrations. The resonant frequency is like when you hit an object and it rings, like you hit this and it ring versus when you hit this and it just thuds. It depends on if it absorbs energy at that point. But the point is that whether it absorbs at that particular frequency or not, the hotter it gets, the more motion there is. And so that was vibrational motion. So let's take a look at one more. To bring up earlier. The modes for ice are a little bit different. You can see. Let's see which one do we want to watch. This one. Okay, so you build up a larger and larger piece of ice. This is what it looks like. All the water molecules are arranged here. There are 2 hydrogens bonded to each oxygen. That is, it's really stuck on there. But they also show on the orientation how the water molecules are held in place there. Okay, so you can see as the temperature goes up, motion goes up. Eventually, what's going to happen? eventually what's going to happen is there's going to be so much kinetic energy, it's going to melt the ice. And that crystal is going to just collapse. Let's see. Still haven't hit the melting point. The ice is getting warmer and warmer, getting closer to 0 degrees C. Ice is going to melt at 0 degrees C. Let's see. On the surface, you can see the ice is melting at the surface of the crystal here. The temperature's got to be a lot warmer. Now we got translational motion there. Right down here, this is strictly vibrational motion, and we got those 3 vibrational modes that we saw in the earlier video, but they're all overlapping now. Now we have translational, and we have, what other type of motion is there? Rotational motion. This is liquid water here. This is called molecular dynamics simulation. So we'll just continue melting the ice. Pretty soon, all that ice is going to melt, and we're going to be left with liquid water. So I'm going to jump forward a little bit. We didn't get all the way. We didn't quite get there all the way. This one we did. Some of the water molecules are vaporizing off the surface. That is evaporating off the surface. So there it goes. Liquid water. And then the same thing, you can see molecular dynamics of boiling water. This is evaporation here. I did grab this earlier, but this is what I'll just show. What happens in evaporation and boiling is we get water molecules with enough kinetic energy to break free from here. You know, they're kind of stuck together. Water molecules like each other, so they stick together. But some of them will have enough kinetic energy, they'll just break free. But sometimes what will happen is they'll condense back into the droplet, come in here and get stuck again. So it's another dynamic situation. And so these are the things we do. We model things to try to visualize them, what's happening. There's another molecular dynamics simulation. So in gases, the particles are moving fast and far apart. They break free. That is, they overcome the stickiness, the attractive forces, which we call. In liquids, they're stuck together. Water molecules are stuck together. They don't have enough kinetic energy to break free in the gaseous state. Some might, like in the evaporation that we saw, but the bulk of them will just stay together. In solids, they just vibrate. There's no translational. And what you saw the ice crystal was very well ordered. That's what we call a crystalline solid. Some solids aren't so well ordered. You know, the position of the molecules are more randomly arranged. The position of the molecules are more randomly arranged, like wax, for example. And wax, all the wax molecules aren't perfectly arranged, so wax doesn't form nice crystals like ice. You know, when you see a snowflake, it looks really nice. Crystalline structure there, whereas in wax you don't really see that. Wax is more of an amorphous solid, which the particles are not quite as nicely arranged. And so this is at the particulate level. So let's again take a look at what Cartolucci says. Particle movement for gases. He says completely independent and in random motion. Each particle may go anywhere in enclosed space. For for me, I just say the particles are no longer stuck together. The particles have full translational, full rotational, and full vibrational motion. In liquids, the particles are stuck together. He says independent beneath the surface, limited to the volume of the liquid and the shape of the bottom of the container. That's particle movement. Particle spacing, close particle interactions are important. Well, for me, the particles are stuck together. There's translational motion, there's rotational motion, and there's vibrational motion. For solids, the particles are stuck together, but they're stuck together so tightly that we lose translational motion. And so they're no longer free to move within the volume there. They're stuck. But they can still vibrate. At a macroscopic level, we'll see the shape. The shape of the gas adopts the shape of its container and fills the container. The shape of the liquid will fill the bottom of the container, like this. The shape of the solid is whatever the shape of the solid is that it's frozen at. This is just an ice cube. It doesn't conform to the container at all. Gases have variable volume. You know, you can compress the gas or expand the gas because there's empty space here, so we can kind of compress it if we want. Liquids we can't compress. Because liquids, the molecules are already touching each other, so you can force them maybe a little bit closer, but not much. And so liquids are what we call non-compressible. Solids are the same thing. You can compress ice a little bit, but not much. It's because the molecules, again, in ice are touching each other. Although ice is a little bit less dense, you know, because of that open structure. Did you see the open structure of ice in the video? Like those big channels. I didn't point that out, but you see how open it is? It's just because of the way the water molecules arranged. It forms a very open, expanded structure like this. This is a very small, thin crystal of ice. We build a bigger crystal of ice. This would be a bigger crystal of ice here. We've got a very open structure. Right, when we're doing certain things, we look. For example, physical properties deal with physical changes. So things like boiling water, evaporating water, melting ice, those are all physical properties and physical changes here. In a physical change, before and after, it's still water. So if we take water and freeze it into ice, is it still H2O? It's still H2O. That's an example of physical change. A chemical change is this. If we take methane and burn it, is it still CH4? No, it's not CH4, now it's CO2. That's an example of a chemical change. A chemical change, we're going to see the chemical identity change. That is, it's going to be replaced, the atoms are going to be rearranged. However, in a physical change, the atoms are not rearranged. So things like boiling, melting, physical, things like combustion, chemical. And we get the properties based on that. We'll have physical properties and chemical properties. So chemical properties would be like combustion, neutralization, gas formation, etc. Physical properties would be like melting, boiling, density, those types of things. All right, I'm going to stop here. I'm out of time, so we'll continue.